Hey guys, sorry I had to bail on you, but I'm on my way to North Carolina, hopefully to meet a new grandbaby. So I'm leaving you with the best I can do while I'm gone. So we're going to pick up where we left off yesterday with the Chapter 6 notes. And if I were there in person, we would just go pick up our calculators and put some data in and kind of play around with it for a while and learn some nifty things about how X's and Y's behave. But since I'm not there, I had to kind of streamline the process to make it go a little bit faster. So I've already put the data in a document, and I have already pushed it out to your calculators. Now, it's on the yellow calculators, the classroom one, so if you got the black calculator, it's not going to be on there. So if you want to actually, kind of follow along, you can go pick up the yellow calculator. If you just want to watch, that's okay too. The big ideas are all that really matter. So I have some data that has been collected about some school grade children, elementary grade school children. I didn't say that right. And I'm not going to tell you what it was. There's a couple of mystery variables. X is a mystery variable, and then there's some context-free variable Y that I'm not giving away just yet. Don't want to spoil the surprise. And we're going to take a look at that data. So I could type it in. I've got a little bit of a glare on the screen. There's not a whole lot that I can do about it, but hopefully it'll be readable. If I go to my home key, and number 2 is my documents. If you have one of the yellow calculators, hopefully it's going to be on there under transfers. And it probably is going to be dated today instead of yesterday. So I put this one on my calculator last night. So it's actually showing the first instead of the second one. When you open up that folder by clicking on it, you're going to have a mystery data Chapter 6 Day 3 sitting there. If it's not there for some reason, just follow along. It'll be okay. Just watch. So I'm going to open that up, and if you get a prompt to not save an old document, just click on no, don't save it. So these are the mystery data. I just call them X and Y for now because I don't want to give away what they are just yet. And these X's I ran, let me back up. I looked at a picture first. So if I go to the second page, I have the scatter plot. So with the exception of this one kiddo right here that has a fairly big Y for his X, and this kiddo over here that has a little bit lower Y for his X than we would see with the rest of the group, there's a pretty strong linear association with these points. These two maybe outlier-ish looking guys muck up the joint a little bit, which is probably going to make our R value not quite as good as we'd like for it to be. So without these two outliers, we'd probably be looking at R value well in the 0.90s. These guys are probably going to show it down a little bit. As a matter of fact, if I go back and look at my spreadsheet, I've actually run some different statistics this time. And I've already done it just because I knew we'd have a hard time getting through it all and fitting it on a video. So this time, instead of running an actual linear regression, I ran something called a 2-variable. So the 2-variable statistics, which is the second option in the stat calculations row in your calculator, will do two things that are kind of neat. One is that it does all the single summary statistics for the X's and the single variable summary statistics for the Y. So I know that the mean of the X's is a little over 5, and the standard deviation of the X's is a little over 1.6. And I know that there were 12 data points. The mean of the Y's and standard deviations of the Y's are computed as well. Maybe at this point it makes sense, finally, why it's not just an S for standard deviation, it's S of a subscript. And the reason the calculator is programmed to notate it SX, SY is so that if you have multiple variables and multiple standard deviations, it's going to tell you which S is which. So that subscript is there to help us keep the two standard deviations straight. There's more variation in the Y values than there are in the X values in this particular set of data. And then if I scroll on down a little bit, I get a bonus. There toward the bottom is actually an R value. So it does give me the correlation. It doesn't give me a line of best fit, but it does give me the correlation. And that may seem like a bunch of jumbled stuff that doesn't have any relationship to each other, but it actually comes in kind of handy for what we're going to do next. So 0.72 is the R value, the correlation. That's a moderately strong positive linear association. And again, it's probably looking that way because of the fact that we have a couple of unusual points here and here that seem to be a little different than the rest of the pattern. Just a couple quickie things that we can review. If we go to the menu and analyze, which is number 4, and if you have your calculators and have the document opened up, you can follow along. Number 6 is regression, and we can show the linear. I'm just going to go with number 1, show linear in x plus b form. And so the equation of this line is about 0.937x, so a slope of close to 1, and a y-intercept of about negative 0.8. So let's talk about kind of the step further of what else we could do with this line than what we've done before, other than just look at it. The purpose of this line is to summarize how the points are behaving and to be able to make predictions with them. There are other things we'll do later as well, but for now we're kind of keeping it simple. So if I wanted to predict what a kid with an x value of 7.5 would be in the y values, I could go to 7.5, follow up to the line itself, and then kind of go over, and I could predict that if a kid's x value is 7.5, his y value is going to be a little more than 6. If a kid has an x value of about 5.5, his y value is going to be somewhere around 4. So the line is useful for predicting y from x. What we have to be careful about is implying that x causes y to happen. So I've got to watch my vocabulary. I can predict y when I know x with reasonable accuracy because I have a reasonably moderately strong association between the two variables. But I can't argue that y depends on x or that x causes y to happen. Any causality, any causation kind of argument, cause-effect argument is going a little bit too far, and we'll see why that is in a few minutes. So I've got one more screen, one more spreadsheet I want to show you. So I built another spreadsheet in, same variable x, same variable y, just copied those over, and I did one more nifty thing. And if I had been here with you, I would walk you through how to do this. We've seen this process before with one variable statistics. So I decided to change the x's to z-scores and the y's to z-scores just to kind of see what that looks like, because it turns out that z-scores give us an r value. If we take a look at some z-scores for all the x's and we convert all the y's to z-scores and we find the products of those and do sort of a pseudo average of them, we end up with an r value. So z-scores really kind of lead to an r value. We don't care about that really yet. We just need to know that r measures strength and direction of a linear association. But if I want to compute a z-score for, say, the x values, I need all the x values in this first column. I'm going to subtract the mean of the x's, which I just copied and pasted in from the other screen, which is a little more than 5, divided by the standard deviation. So this is our z-score formula, and I ran it for all of those values. So we have the z-scores for all the x's, and then I did the same thing for the y's. So calculated the z-score y minus y bar. I copied from the other screen and the standard deviation of y, and got a bunch of y values. And if you kind of scroll through the y values and x values in z-score form, you'll notice that most of them are within one unit, one standard deviation of the mean. We got one kind of oddball that's 1.9 standard deviation from the mean there. That's one of the outlier looking fellas. And then this one right here is about 2 standard deviations away from the mean in the x direction. So we can have points, since we're in 2 variable land now, that are kind of farther from the mean. This guy's unusually far from the mean because he's more than 2 standard deviations out, but only in the x direction. This guy's almost 2 standard deviations out in the y direction. We don't normally deal with an actual outlier rule, and we don't normally bother to really examine these on a regular basis. For the purposes we have for linear regression, we normally just care about looking at the picture and saying those 2 points are kind of out of line with the rest of them, and that's good enough. But for this one time, I wanted to take a look at these while we had the chance. Okay, so once I converted them to z-scores, I decided to plot a graph of those. So we already have that graph on the screen. If you do Control right and flip the page to page 4, there's a split screen of the two different scatter plots. One is x versus y in raw score form, and the other is the z-scores of x's and the z-scores of y's plotted together. And if you take just a brief look, it should jump out that they're exactly the same shape. That shouldn't be a shocker at this point. We saw that that was always true for one variable data. If you have one variable data and you convert it to z-scores, the picture doesn't change, only the scale changes. All z-scores do are eliminate units. Z-scores are a unitless measure. And because R values are actually computed from z-scores, that means R is also unitless. So R has no units. Okay, so it's very much like Z in that it's kind of a generic number that's still just kind of, we still have limited understanding of, but it's okay because it'll get better. The other thing that you might notice is see how some things line up. So you have a mean of 0 here, and that lines up with about here. See where those 2 points that are like, you know, right above each other. If you line that up here, it's a little bigger than 5, like 5.08-ish. Oh yeah, that's right, that was the mean of the x's. And the mean of the y's was 3.9-ish, so 3.9-ish is around here. Well, my screen keeps wanting to go to sleep. And that lines up with the 0 line down here. So as it turns out that in the x direction the mean goes to 0, and in the y direction the mean goes to 0, and the standard deviations are 1. So we're looking at the same patterns of how z-scores behave, but it's happening in both directions now. So in both the x direction and the y direction, 0 is your mean, and your standard deviation is 1. And just to kind of drive home a point, if I go up to this top graph and click, and if I go to Menu, and Analyze, and Regression, number 6, and show the linear there. So there's the line of best fit. And then go down to the bottom half of the screen and click, and drop a regression line there. So Menu, Analyze, Regression, and number 1, show linear. Okay, notice that they look a whole lot alike. And not only that, but something really cool happens here. Notice that this z-score graph down here, the line goes through 0, 0, which means this line of best fit, it goes through the mean, comma, the mean, which means up here, somewhere around right there, this line in the real world context units, whatever they are, this line is actually going to go through 5.08, comma 3.9 something. This line goes to the mean, comma the mean as well. Turns out that's true for all computer generated lines. The best line, the best fitting line for any linear set of data is going to pass through the mean of the x, comma the mean of the y. And that's a really big idea that we'll kind of leap on in chapter 7 and use to write equations by hand, because that gives us a key point every single time that we need to put on that line of best fit. Okay, so I'm going to lay that aside and let's just do kind of a summary. We are going to come back one more time, I think, before we quit with this graph, so let me just lay it aside. Right, so we looked at the data, don't really need to write anything down there, but let's go to properties, take 2. Correlation doesn't have units because technically correlation is computed from z-scores. It's happening in the background. We're not looking at that. The formula is a little bit ugly. We'll take a look at that another day. It's not a percentage. Percentages are technically kind of units, and there are no units. It's just a number between -1 and 1. Correlation is not affected by changes in units, just like z-scores. So if you take your units away and you make it unitless, like converting to z-scores, then you're going to get the same picture, just a different scale. If you convert ounces to pounds, same scale. You convert years to days, same R value, not same scale, same R value. So R does not change when you manipulate your data by changing units. Also, if you switch your x's and y's and put your y on your x-axis and x on the y-axis and recompute your regression line, it'll still have the same R value. And that's this last piece. If you switch x and y, you still get the same R. You don't get the same regression equation, but you do get the same correlation because the relationship between the two variables really doesn't change. And then last but not least, this is a biggie. Correlation. Just because you have a strong correlation, a high R value, doesn't mean that there's a cause-effect relationship. Okay, now there's a reason for that, a really big reason. So let's go back here one more time before we go to the next slide. Okay, let's go back to, I didn't mean to do that. Let's go back to the first graph, which is this one. So I'm going to let you in on what the mystery variables are. So these are grade school children. In the x direction, we're measuring shoe size. In the y direction, we're measuring reading level. So this young fellow right here, let me just hover over this one. Oh, I can't read that one. Let me hover over this one. This young fellow right here wears a size 4 shoes and reads on a 2nd grade level. This fellow right here wears size 5 shoes and reads on a 5th grade level. This fellow way up here wears a size 5 shoe and reads on 8th grade level. So he's got little feet, but he reads really well. So if this is a shoe size and this over here is reading level, can I argue reasonably that because this kid over here has big feet, he should read better? So does having big feet cause you to be a better reader? And that's a no. That's not true. Because there's this thing in the background that we're not talking about, sort of the fly on the wall, this lurking variable that's in the background that's working on both the x and the y. It's called age. The age of the child has effect on shoe size. The older you are, the bigger your feet get. For school age children, that tends to be true. And the older you get, the higher your reading level should also be true. There's some anomalies. Different kids kind of fall, along the lines a little differently. There's some variation always, but that third variable, age, is impacting the x and impacting the y and causing them to behave the way that they do. And it explains what appears to be a strong association between x and y. X doesn't cause y to happen. There's a lurking variable that's acting on both of those. So that's what this next slide summarizes. A lurking variable is a variable other than x and y that simultaneously affects both variables, accounting for the correlation between the two. So this is why, this is the reason, let me write this down. This is the reason that we never, ever, 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 ever argue a causal, like cause-effect relationship between x and y. Even if the correlation is 1, even if it's perfectly related, the x and the y are perfectly related, you still can't say x causes y. You just know that there's a very strong relationship between them. Very high predictability. If you know x, you can predict y very, very well. That's all you really know. So you have to be very, very careful about your language when you talk about an association between two variables. Never, ever, ever imply that one causes the other, one leads to the other, or that you can use one to argue that the other one needs to happen. All right. So now let's just look at some examples of things that you might be asked to deal with. Basically, these are things that could go wrong, things they could try to trick you with in terms of wording, and we're going to learn how to not fall for it. After conducting a survey of his students, the professor recorded that there appears to be a strong correlation. There's that word correlation. Now, correlation special is a number, and it's a number that describes the strength and direction of a quantitative pair of variables. Correlation between grade point average, that's quantitative, and whether or not a student works. Okay, here's a problem. Whether or not a student works, is that quantitative? Can you graph that on a number line? They work or they don't work is what it sounds like. So this is actually categorical. And because that's categorical, using the term correlation is wrong. It does not apply. So comment on his observation. This is what we're going to say. The word correlation should be replaced with association, since whether or not a student works, is categorical. So be careful about throwing around the word correlation. It seems that it happens on a regular basis in the scientific world. We are going to have to do better than that. We have to use it appropriately. Do not use the word when you're talking about categorical variables. All right, the next one. What is wrong with each statement? So these are going to go pretty quickly. These are easier. The correlation between Olympic gold medal times for 800 meter hurdles. Well, those are times. Those are done in probably seconds. That sounds quantitative. And year. Well, year is quantitative. You can put those on a number line. Is negative 0.66. That's a reasonable R value. It's between negative 1 and 1. Seconds per year. Oh, that's what's wrong. Those are units. Correlation doesn't have units. So correlation has no units. That's what's wrong with it. Next one. Correlation between Olympic gold medal times, that's quantitative, for the 100 meter dash and year is negative 1.37. That's too small. That can't be. That's the problem. Correlation cannot be smaller, or we'll say less than negative 1. Correlation is always a number between negative 1 and 1. That's not possible. They're trying to trick you. Do not fall for it. Remember the next one. Since the correlation between Olympic gold medal times for the 800 meter hurdles and the 100 meter dash is negative 0.41, okay, that's a reasonable R value. The correlation between times for the 100 meter dash and 800 meter hurdles, so it sounds like they're switching X and Y, is positive 0.41. Okay, here's the problem. Switching X and Y does not change the correlation. So switching variables does not, sorry, my hand's in the way, change R. R would still be negative 0.41. Does not change. R is R is R. The only way you can change R is to actually add a data point, take out a data point, or change a data point to different numbers. One data point or 2 data points, but not the whole thing. If we were to measure Olympic gold medal times for the 800 meter hurdles in minutes instead of seconds, okay, so that's a unit change. The correlation would be negative 0.66 divided by 60, or negative 0.011. So if you change minutes to seconds, you divide by 60, right? Well, you do your data, but R doesn't change. So R would still be negative 0.66. R does not change when units change. When the data's units change. R is R is R. It's like Z. It is unitless. And one more. Almost got this one. Last one. A school board study found a moderately strong negative association between the number of hours high school seniors worked at a part-time after-school job and the student's GPA. Okay, both of those are quantitative. Of course, we're talking about an association. So, pretty good indication that as number of hours worked goes up, GPAs go down. That's what we're seeing. Hoping to improve student performance, the school board passed a resolution urging parents to limit the number of hours students be allowed to work. Okay. Does this statistical evidence exist to support this resolution, and explain? Okay, the big simple answer is no. Because just because there's an association doesn't mean there's a causal relationship. There's no evidence that it's the after-school job that causes the GPA to go down. Okay, so no, there is no evidence that working more hours causes lower GPAs. There could be lurking variables. And we may never know what those lurking variables are. Just because we can't pinpoint them doesn't mean they don't exist. So a lurking variable could be as simple as this senior is working a part-time job because their family needs help financially, or because maybe family doesn't have the financial ability to help them with senior expenses, with vehicles, with college things coming up. And those things, those worry and stress and just situations could also impact the GPA in a negative way. So there could be lurking variables that are affecting both the needing to work or wanting to work and how the GPA is looking. So since those always could potentially exist, we just always want to realize that those could be working in the background. All right, you have the last homework assignment, the day 3 assignment there on your PowerPoint. Work away at those. I'm sorry I can't be there for you. We will need to do a quiz on Thursday, and you can turn your homework in. And after the quiz tomorrow, you will just do some reading. I'm not even going to try to push you on from there because I don't have time to prepare enough. And I'm going to try to leave you a video for Friday just so that we don't lose that day to get us started on Chapter 7. So the way it's looking, I'll probably see you on Monday. So have a good weekend.